Okay, so we're going to continue with this problem. The last bit's actually very simple, but I think there maybe just needs to be a bit of discussion about quite why we're doing what we're doing. So we're looking for the shear center of an open beam section like this. Now we know that when we've got a section with symmetry, so this has a line of symmetry running down the center, the shear center must be somewhere on this line of symmetry. So it's either on the line of symmetry inside of the C section, it's either on the line of symmetry on the centroid of this element, or it's on the line of symmetry outboard. Now from the images that we've looked at, we know the shear center has to be over this side, has to be somewhere out here at a distance to be determined. And let's just have a think about why that is. So to determine the shear center, we have to load this section somewhere in a direction normal to the line of symmetry. It doesn't help us loading it parallel to the line of symmetry. We load normal to the line of symmetry. So if I load here, say this could be position 1, or if I load inside and position 2, and we could do the same thing for the centroid, I'm just not going to bother. We know that those internal shear flows, the internal action flows, are going to exist like this. So we've got the vertical one that's aligned with the main member because it's aligned with the shear force, whether I apply it here or here. Let's just write this as Vy. We know that from the continuous distribution that we have to have, the shear flows have then got to have this direction. So it follows that if I load this C section vertically and in a positive direction, I will always have a sort of clockwise motion to the internal action shear flows. Now, in the bit of theory that we went over, and I then said we could sort of almost forget about, the bit that we actually worry about is the reaction shear flow. So the reaction is the bit that actually causes the reaction back on the structure. And what we really want, let's just give these some names. Let's say these are QS is the action shear flow. Let's call this QSR, which is the reaction shear flow. So these are shear flows which accordingly have units of newtons per meter. So to turn these into forces, we integrate them along S. So it corresponds that we've got some force acting this way, some force acting this way, and some force acting this way from the actions. And then the reactions would be a force here, and a force here. So these action flows are just a consequence of loading it with this. They are how that internal structure propagates that flow, propagates this force back to the reactions. The blue one is the reaction on the structure. So there is a moment that's going to be produced by this and a moment produced by this. So wherever we evaluate them, we could write this as M, let's call this MV. And then, just bear with me 1 second. And there could also be a moment caused by these blue arrows here. So by this one, by this one, and by this one, which is just the integrated load. Now, the only place at which those are, if these equal 0, then we have no torsion in the entire structure. We've got no net moment as a consequence of the internal flows, or sorry, the applied load and the applied and the reactions because of them. That's this situation here, and this only happens if we load at the shear center. If we don't load at the shear center, then we see, for example, if we let's draw a couple of other. No, let's go ahead with this. So, because let's write this down. QSR with the reaction is equal to the opposite of the internal shear flows, which are the red ones. I'm losing my colors here. We can actually just say that QR is equal to minus MQ, which would be the integrated moment, the moment due to the internal red arrows. then we can just replace this expression up here with mv is equal to mq if and only if loaded at the shear center. Okay, so this is the equation we can use. So I bring in those blue arrows just to help us think about what's going on with the structure. We don't actually use them, and we don't actually use this. We don't calculate these. It's just a way of telling us why this equation helps us in this case. So let's think about three cases. Now we're going to imagine that we've got three different C-beams. We're going to load them in different horizontal locations, but we're going to load it with a vertical force. So if we're loading it with a vertical force, we're always going to have the same shear flow distribution. Because if we're loading with a vertical force, we remember that we don't care where that force is being applied in terms of how these shear flows actually get propagated. And let's just go back to the equation that we were using to calculate those. So remember, those internal shear flows come from this expression here. There's nothing in here that is dependent upon x, okay, except possibly y, which is then a function of s in some cases, but there's nothing here that matters where Vy is being applied. So as long as we apply a vertical force to this structure, a vertical shear, we're always going to get the same internal pattern here. So that means that the moment produced by, this would be MQ in this case, MQ would be in that direction, MQ would be in that direction, MQ would be in that direction. So remember that for the condition of the shear center, so MV is equal to MQ if and only if at the shear center, then that means we know that we cannot load, for example, here, because no matter where I evaluate a moment here, I'm always going to get a counterclockwise moment due to this part here. Okay, if I load outside of the section somewhere, I'll get a moment in the same direction, so this is pretty good. Imagine now if I load here exactly at the centroid, if I were to evaluate moments here, say, then I get no moment due to the applied shear force, but I still get a clockwise moment due to this one. So it can't be that, can't be that, and this is why the shear center must be outside of the C section in a shape like this. So that's just a reminder of why we're going through that. I've gone through this with a couple of students, what shear center is. If you're still not comfortable with what shear center is precisely, then let me know and I'll do another video refresher on that. But we got to this point. So we had determined the three shear flows. So we've got 1, 2, 3, and 4. Those were the node numbers that I gave. We said we had some linear distribution here, some quadratic distribution here, and a quadratic distribution here. And because we loaded vertically, let's say that we loaded at distance E away from the centroid of this vertical member. So that means that my shear flows are going in this direction. So we now need to find a condition for which the moments due to these three shear flows equal the moments due to this. Now I can pick anywhere to evaluate these moments. I could evaluate my moments here, for example. This could produce a moment, this could produce a moment, and this could produce a moment. I could evaluate my moment here. Now this force, because it's a long member 1, 2, could no longer produce a moment. This one could, and this one could. The sensible place to load this and choose the loading is either here or here for this one, because if I choose to evaluate moments here, this shear flow and the corresponding force cannot produce a moment here, so I don't need to care about it. And again, this one exactly the same. So I'm going to choose to evaluate moments here. So we choose to evaluate moments here because then we only need to care about this one shear flow. Because only shear flow QS1 can produce a moment. And if we're uncertain about why, then let's just remind ourselves exactly what these shear flows are. Even though I draw the arrows next to them, we've got to remember that shear flow is newtons per meter acting along in this direction. So when I integrate these to produce a single force, it then would just be a force acting somewhere along this body. Okay, because it's acting along here, we don't actually define where it acts. It's a distributed force acting along this length. But if I was evaluating moments here, the line of action of this force is through that moment collocation point, so it can't produce a moment there. So let's go back over here. So we evaluate moments here because only shear force, or sorry, only shear flow QS1 can produce a moment. So that's the only one we need to remember, which is good because I had forgotten the others, and I've got the other ones. I've got QS1 written down here. So QS1 for us was equal to 6V. So this is my V up here. 6V divided by h squared 1 plus 6B on h multiplied by S1. Okay, so just remember this was the base. It's terrible B. This is at an angle, so it's kind of hard drawn. And this was my height in this case here. So we can then work out the moment at this point here. So it's going to be whatever the force is multiplied by the height, because that's the moment arm there. So we need a corresponding force associated with this. So we need a force associated with QS1. Let's just check that I use the right symbol because I don't want to confuse any nomenclature here. Yeah, okay, so we're going to call that FQ1, yes. Okay, so that is just going to be the integrated force from here to here. Okay, so remember that ordinate S1 simply started at 0 here, becomes B here. It's just a line. It's just this displacement along here. So this was my S1. So that's then the force associated with that one. Let's put, we should be able to see quite simply what that's going to be actually. So okay, let's put QS1 in here. Well, I can see here that this is just some big non-function of S1 multiplied by S1. So this is just going to become 6V over h squared 1 plus, move this down so I can write on it properly, plus 6B on h, and then we're going to do the integral from b to 0 of S1 ds1, so let's just do this integral separately. This is just going to be b squared on 2, isn't it? Okay, so we have b squared on 2 here. So let's write this up fully now. This is going to be 3 v b squared divided by h squared 1 plus 6b on h. So that is the moment, sorry, it's not the moment, that's the force being produced along here. So we know there is a force here, FQ1. So the moment that's going to produce is just going to be taking that force and multiplying it by h. So the force at node 3, remembering our nodes were 1, 2, 3 and 4. The force at node 3 is simply what we've just done above multiplied by h. I'm not going to write that down just yet because I don't need to write it. So we know this has to be equal, if we're loading at the shear centre, to the moment produced by this. So the moment at 3 produced by our loading v, which is just an arbitrary loading v, is going to be v multiplied by e. So this must be equal to v multiplied by e if at shear centre. So then we can write this out. V multiplied by e is equal to fq1 multiplied by h. So it's this bad boy multiplied by h, which just gets rid of the h squared on the bottom. Okay, and we see these v's cancel. E is equal to 3b squared h 1 plus 6b on h. Okay, so that is the location of the shear centre for this object. Okay, and this was defined such that I gave this distance defined to the left of this centre. And if we'd done this differently, if we'd done here and we decided to load it here and called this distance E, for example, done the exact same thing, we would have found that we'd have to be careful with moments. So you would have remembered that the shear flow would be exactly the same. So we'd have arrows here and arrows here. So MQ would be clockwise, whereas actually the moment because of this would be counterclockwise. So then we'd end up with the exact same thing. E would then be equal to, it would be equal to this expression, but we'd have a minus sign here. And that's just because of the way that we've defined this distance in this problem. Okay, so if you choose the wrong side of whatever you're looking at for your definition, then just you'll get a negative number out the end. Okay, so we've gone through and developed this shear centre for an open section. Gone through and used methods that are mainly new to you guys, but hopefully building upon some concepts we've had before. I'm going to, let's just have a look in the accompanying notes a second. You guys should be able to now tackle problem 2.2 and problem 2.3 as well, but there's some different things to do in there. Okay, so I'm going to ask you guys to go through them. I will provide some solutions to these, but I promise you, if you look at the solutions without having attempted it yourself, then you will probably fail your examinations because you need to be able to understand the problems that you're facing. Okay, so once we've done that, next week I'm going to release some more examples for those two in here. I'll probably actually release the solutions towards the end of next week. I'm going to move on to closed sections now. So we're going to look at closed sections next week, and we might get a chance to look at actual torsion, how we calculate the torsional stiffness. Because if we can calculate that, then we can just replace our aerofoil. We can just replace it with a torsional spring with some constant. Okay, and we're going to use this when we look at divergence. So it'd be nice to be able to do that. We'll move on to that next week. So we've done all of the stuff with open sections. Now with open sections it was nice and easy because we started at this open section. We start at the open end and we know we get a shear flow distribution that looks like this. So by definition we have to have 0 here and here. What about if we've got a closed section? There's nowhere to start the problem yet. So what we're going to need to do is we're going to need to make somewhere to start this problem. So we're going to do that, and that's what we'll move on to next week. Guys, I hope you're all having a wonderful time, enjoying these wonderful videos. Like I've said before, please, you guys know I'm going in May. I'm going to keep these lectures up anyway, so do the old like and subscribe, and I would appreciate it very much. Guys, have a wonderful weekend. I'll see you next week.